Welcome to the Global classes. Today we will discuss about the jet propulsion of the ships. In this case we will be having the two cases. The case one will be when the jet orifices are at right angles to the direction of motion of the jet, and the case two will be when the inlet orifices are face the direction of the ship. So in these two cases we will derive the impulse force or the propulsive force, and then we will find out the efficiency of that system, and then also we will find out the use of it, and then we will take some numericals in this particular class. So the first case we consider for the jet propulsion of ships when the inlet orifices are at right angles to the direction of motion. This is actually the example of the impulse momentum equation we are utilizing to find out the force and by which we can run the ship. So in this particular case, here in the case 1, the ship is moving say from the right to left with the velocity u, and the jet is going out with the velocity of the v in the water only. And the water is taken from the center point of the ship, that is the sides, that is known as the inlet orifice. From this we are taking the water, and this is known as the end ship points. So from this it is taking, and the ship is moving in this direction, that is known as the bow end or the front end of the ship, and the ship, the tail end, that is the back end, is also known as the stern. These points you have to remember, because in the exam it may be there that bow or the stern or the end ship or end point is given instead of the given as the front, back or the midpoint. In this case, what we do, we take the water from the sea, from these pipes, inlet orifice, and then we put a centrifugal pump here, which increases the kinetic energy of the water and injects it into the water with a high velocity. And that high velocity water, when it goes out in this liquid, it gives the thrust, that is the propulsive force. So we will analyze what is the propulsive force. To analyze this, we are going to use the impulse momentum equation. So first we will try to find out the velocity of the jet with respect to ship. So that will be given as Vr, velocity of jet with respect to the ship. It will be equals to V plus U, and will be named as Vr, because the jet is going in this direction, the right way, and the ship is moving in the left direction, so it will become V plus U. Otherwise it should have been V minus U. So this will be V plus U. Then the area of the jet is say A. Area of the jet is A. This is the area of the jet A. And if you want to find out the mass flow rate issuing from this jet, it will be equals to rho into A into Vr. Rho is the density of the water, A is the area of the jet, and Vr is the relative velocity of the jet with respect to ship. So this is the mass flow rate, and this can be written as rho A V plus U in terms of absolute velocity of jet plus the velocity of the ship. So the propulsive force will be given as mass flow rate of water into the change in jet velocity. So the mass flow rate of water is rho A V plus U, and change in velocity, the initial velocity of the jet is Vr, relative velocity, minus final velocity
propulsive force. This can be written as rho A V plus U into VR, we can write as V plus U. So V plus U minus U. So this will become rho A V plus U multiplied by V. So this is the propulsive force we have. Now if we want to find out the thrust or the propulsive work per second, then the propulsive work per second will be equals to propulsive force multiplied by the force by which it is moving per second, that is the velocity of the ship. So it will be equals to rho A V plus U into V into U. So this is the propulsive work or the thrust work per second. Now if you want to find out the efficiency of this jet, so we have to find out what is the kinetic energy we are supplying to the jet. So the kinetic energy which we are supplying to the jet is equals to 1 by 2 rho A VR, that is the mass flow rate, this is the mass flow rate, 1 by 2 and into V square, so it is VR2, VR square. So it becomes 1 by 2 rho A VR cube. This much kinetic energy we are supplying to the jet. So the efficiency of propulsion will be equals to the work done per second, that is rho A V plus U into V into U divided by the kinetic energy we are supplying 1 by 2 rho A VR is nothing but V plus U whole cube. So this is the kinetic efficiency of this. If you solve this, then it becomes 2 into V into U upon V plus U square. So this is the efficiency of the propulsion. So the efficiency of propulsion is given as 2 into Vu upon V plus U square. Now if you want to find out what is the maximum possible efficiency of propulsion for the given value of V. So to find out that, we will differentiate this efficiency of propulsion with respect to the ship velocity and then we will equate this to 0. So if we differentiate this one, 2Vu upon, that is D 2 into Vu upon V plus U square D upon Du. So if we differentiate this one, we will get, and we will equate this with 0. So it will become V plus U square into 2V minus 2Vu into 2V plus U equals to 0. So this can be written as V plus U into V plus U into 2V minus 4VU equals to 0. So if we differentiate, we will get this, and equating with the 0, so we will get this one. So V plus U equals to 0, either this should be 0 or this should be 0. If it is 0, then V will be equals to minus 2, that is not possible. So this eliminates the choice. Then V plus U into 2V minus 4VU should be 0. If you say this is 0, then it will be 2V multiplied by 2V we are taking out, so V plus U minus 2U equals to 0. So V cannot be 0. That means V plus U minus 2U should be 0. From this, V minus U equals to 0 or U should be equals to V. So if U is equals to V, then we will have the maximum efficiency. And if we wish to find out what is that value maximum, so to find out that, we will substitute the value of U in this equation or value of V in this equation. So it will become 2 into U upon U plus U whole square. So it will be 2U square upon 2U square. So it will be equals to 1 by 2 or 50%. So when we are considering this case, when the inlet orifices are at right angles to the direction of motion of the jet or the direction motion of the ship, in that case the efficiency of propulsion will be maximum 50%. If we consider the losses in this pipe are negligible or 0. So this is the case 1. So I am writing down the formulas which we are using here: mass flow rate, force, work done per second, kinetic energy supplied per second, and the efficiency. And then I am writing down the maximum value is when U equals to U and it is equals to 0.5 50%. So this is all about the case 1. These results were derived. Now we consider the case 2. Now the case 2, when the inlet orifice are facing the direction of the ship, that is, this is the inlet orifice which is facing the direction of the ship. So here this arrow will come on here. This is the inlet orifice and this is the here. And this is in the top view. In the front view, you can see the water is entering from the direction of the ship, and it is a centrifugal pump which is supplying the energy. So the kinetic energy of the water increases and it is going into the sea and generating the propulsive force. So in this case, we will try to find out the mass flow rate, force, work done, kinetic energy, and the efficiency, and the condition when the efficiency will be maximum and the value of the maximum possible value. So in this case, the V is the absolute velocity of the jet as we have taken. U is the ship velocity by which it is moving. Vr is the relative velocity of the jet with respect to ship, that is V minus U, because both the velocities are in the different direction. The U is in this direction and V is in this direction. So relative velocity will become V plus U as it was in the case 1. Now area, we have taken A of the orifice at the exit point from which the jet is going out. So the mass flow rate will be equals to the same as we have taken in the earlier case. The mass flow rate will be same as rho A into Vr. The propulsive force will also remain the same, mass flow rate multiplied by the change in velocity. So the change in velocity will be the same as Vr minus U. So it is Vr minus U that is giving you the value V. So this is the mass flow rate. Then the work done per second will also remain the same. Work done per second will also remain the same. V rho A V plus U, that is Vr multiplied by V. So this is the force multiplied by the distance moved per second, that is the ship velocity. So work done is also same in the case 2 as it was in the case 1. Only the change in kinetic energy or the kinetic energy supplied by this pump will change. It will be as the water is coming with already a kinetic velocity of mu square by u, and it is going out with the velocity of mvr square by 2. That is, this is the exit velocity and this is the inlet velocity in this case. So the pump is providing the kinetic energy of the difference of these two. So 1 by 2 rho a Vr, that is the mass flow rate, multiplied by the outlet velocity, jet velocity is Vr, so Vr square minus the initial velocity is u. So it is Vr square minus u square. So this is the kinetic energy which we are supplying in this case. But in this case, the case 1, this was the kinetic energy. So to find out the efficiency of the jet or the propeller, we have the work done per second divided by the kinetic energy. So it will be rho a v plus u into v multiplied by u divided by this 1 by 2 rho a Vr, that is v plus u multiplied by here v plus u square minus u square. So rho a cancel, v plus u will cancel, this 2 will come upside, so 2v into u upon v plus u square minus u square. So we will get this one. When we solve this further, it will become 2vu upon, if we open up v square plus u square plus 2vu minus u square. So u square will cancel out. So we will be left with 2vu upon v square plus 2vu. If we take out the v also common, and from this, so it will cancel out. So we will be left with 2u upon v plus 2u. That is the maximum, the efficiency formula we will get in case 2 when we are taking the water from the front end or the O end and leaving this at the back end or the stern end. Now, this is not possible to find out the maximum efficiency condition in this case. So what we will do, we will take, if the value of u equals to v, in this case the efficiency was maximum, so we will try to find out if the value of u is equals to v, then what is the efficiency here we will get. So again we will substitute for uv or for v, we will substitute u. So say 2u upon u plus 2u, so it is 2u upon 3u, so u will cancel out, so it will be 2 upon 3, that is 66%, 0.6%. So this is the maximum possible efficiency in the case 2 when we are taking the water from the front and leaving it at the back. So this way, if we compare these two, then this option is having the more efficiency compared with the first case. So this is all about the jet propulsion of ships. Then we will consider 3-4 numericals on this. So this particular topic will be over.
Question number 1. A ship driven by reaction jets and discharged astern is found to have a resistance to motion of 2950 Newton when moving at 30 km per hour. The velocity of jet relative to ship is 18 meter per second. Determine 1. The number of jets if each jet has an area of 85 centimeter square. 2. The power required to work the pump and the propulsive efficiency for the following cases. A. inlet orifice at right angles to the ship motion, and B. Inlet orifices faces the direction of ship motion.
Before we go for the numerical, here I have written down the summary of the two cases. In the case 1, mass flow rate, force, work done, kinetic energy supplied, the efficiency formula, and the maximum possible value. In case 2, the mass flow rate, force, work done are the same, only the kinetic energy supplied is changed to this value, and the maximum possible value when U equals to V is the 66.6%. So now we consider the question number 1. Resistance to the motion of this jet is 2950 Newton. Resistance to the motion is given as 2950 Newton. Then it is given that the velocity of the ship U is given as 30 kilometer per hour. So we have to convert this into meter per second. So it is 30 into 1000, that is meters per hour. So divided by 60, divided by 60. So it is equals to 8.33 meter per second. It is given. The velocity of the jet relative to the ship, is given in this question is equals to 80 meter per second, and we know that the relative velocity is v plus u. So we know the value of u, so we can calculate the value of v, the absolute velocity of the jet, as vr minus u, and substituting 80 minus 8.33, so it becomes 9.67 meter per second. Now we have the area is also given. Area in this question is given as the 85 centimeter square. 85 centimeter square. So we will convert this into meter square. So it will be 85 into 10 to the power minus 4 meter square. So this is the area given. What is the area required as such? Because to solve, we will use the equation, the force exerted by this jet. This is common in both the cases. So force is given as rho A VR into V. We will substitute the values. The force is given as 2950 multiplied equals to 1000 multiplied by the area. We are finding out the total area multiplied by VR. VR is given as 80 multiplied by V. V is given as 9.67. Get calculated meter per second. So by this we can calculate the value of area. This is coming out to be 0.01695 meter square. So this much area we require to get this thrust for these given velocity conditions. So, but we know that the one jet is having this much area. So the number of jets required will be the total area required 0.01695 divided by the area of the one jet, 85 into 10 to the power minus 4. So it is coming out to be 2. So we will be taking the 2 jets of this area. If the value of this comes out to be more than 2, say 2.1 or 2.2, then in that case we will write the number of jets required is 3. Or if it is coming more than 1.1, then we will say it is 2. So in this case it is the 2. Now we have to find out the power required to drive the pump and the propulsive efficiency. So the power required to drive this pump is work done per second, rho A V plus U into V into U. It is common in both the cases. So power required will write down rho A V plus U multiplied
area what we have calculated, this much area is required. So into 0.01695 multiplied by V plus U, that is given as VR. So multiplied by 18 multiplied by V, it is 9.67 multiplied by U, it is given as 30 kilometer per hour, that is 8.33 meter per second. So the power required is coming out to be 24573.5 joules per second, or we can write as 24573.5 watt, or we can write this as 24.573 kilowatt. So this is the power required to drive this ship. Now we have to find out the efficiency. So to find out the efficiency is in case 1 and efficiency in case 2 are different. So we will solve it separately. We know that the power required is this much. So we will utilize this equation again, the value. So efficiency in the case 1 is the kinetic energy supplied. First we will find out kinetic energy supplied is equal to 1 by 2 rho A V plus U, that is VR cube. So we will substitute the value 1 by 2 into 1000 into the area is 0.01695 multiplied by VR, is given 18 cube. So the kinetic energy supplied in the case 1 is 49426.2 Newton meter per second. Okay, so the efficiency in case 1 will be work done, that is 24573.5 divided by kinetic energy supplied 49426.2 is equals to 49.7%. So you can see here the efficiency is coming out to be less than 50%. So it is okay, because in this case the maximum possible efficiency was 50% and here it is coming out to be 49.7. Now in case 2, if you consider the kinetic energy supplied is given by 1 by 2 rho A V plus U, that is VR multiplied by VR square minus U square. So we will substitute the values 1 by 2 into 1000 multiplied by 0.01695 multiplied by VR, that is 18, it is given 18 multiplied by 18 square minus U square, that is 8.33 square. So when we solve this, we will get this result equals to 38840.9 Newton meter per second. So the efficiency in this case is output, that is work done per second, 24573.5 divided by the kinetic energy supplied, that is 38840.9. So it is coming out to be 63.26%. So in this case also you can see the efficiency maximum possible was 66.66 and it is coming out to be 63.26. So it is okay. So that way we have taken the question number 1.
Question number 2. A small ship is fitted with jets of total area 0.65 meter square. The velocity through the jet is 9 meter per second and speed of the ship is 18 kilometer per hour in sea water. The efficiencies of the engine and the pump are 85% and 65% respectively. If the water is taken amidship, determine 1. The propelling force and 2. The overall efficiency. Assume the pipe losses to be 10% of the kinetic energy of the jet.
Question number 2, it is given that the total area of the jet is 0.65 meter square. Then the velocity of the jet relative to the ship is given as VR equals to 9 meter per second. 9 meter per second. Then the speed of the ship is given in this question is equals to 18 kilometer per hour. That if you convert it into meter per second, it is 5 meter per second it is given. Then it is also given the efficiency of the engine is 85% and the efficiency of the pump is given as 65%. Then it is also given that the pipe is having a 10% loss of kinetic energy. So the pipe loss is given as HF is equals to 10% of the kinetic energy, okay, of the jet. So the kinetic energy of the jet, if we consider per kg, then it will be the kinetic energy will be 1/2 Vf square, Vr square, that is the kinetic energy of the jet, and there is a loss of 10%, so it is 10/100, it is the loss. So it will be equals to 1/20 Vr square. This is the loss in the pipe. Okay. Now, how to solve this question? In this question, it is given that you are having an engine. This engine produces some work, and this is having the efficiency of 85%. So whatever it will give, it will be received by a pump, and this pump will have an efficiency of 65%. So the 65% of it will supply to the water. So here you will have the kinetic energy, and from this, when this is going out, before that you will be having a loss of 10%. Okay, then here you are having VR square by 2. This is the kinetic energy you are having. So अब हमको अगर ये काइनेटिक एनर्जी चाहिए है यहाँ पर, तो उससे 10% ज़्यादा काइनेटिक एनर्जी हमको यहाँ पर मिलनी चाहिए. अब इतनी काइनेटिक एनर्जी हमको यहाँ चाहिए या इतनी एनर्जी चाहिए, तो वो एनर्जी ये पंप से मिलनी चाहिए. लेकिन पंप को अगर हम 100 देते हैं तो वो 65 ही हमको आउटपुट देता है. ठीक है, तो वो जो 65% है वो इस टोटल के बराबर होनी चाहिए. अब पंप की अगर हम बात करें तो इंजन जितना प्रोड्यूस करता है उसका 85% ही पंप को देता है. तो जहाँ जितना चाहिए उसका 85 और 15% और उतना इंजन को प्रोड्यूस करना चाहिए. तो इस तरीके से हम लोगों को कैलकुलेट करना पड़ेगा. सो फर्स्ट विल कैलकुलेट व्हाट इज द काइनेटिक एनर्जी हियर ऑफ द जेट वी नीड, दैट इज 1/2 Vr स्क्वायर. उसमें हम इसका 10% दैट इज 1/20 Vr स्क्वायर ऐड कर देंगे. तो ये काइनेटिक एनर्जी या इतनी एनर्जी ये पंप यहाँ पर देना चाहिए. ठीक है, तो इसको हम लोग ट्राई करते हैं. सो फर्स्ट वी कैलकुलेटेड द पाइप लॉस दैट इज 1/20 Vr square. Now we know that Vr is nothing but V plus U. We know the U, we know the Vr, so we can calculate the V. V will be equals to 4 meter per second. Okay. Now the propelling force F. Propelling force F is given as rho A VR into V. Rho A VR into V. So we'll calculate the value of this propelling force, that will be equals to 1000 multiplied by the area of the jet, 0.65 multiplied by VR, that is 9 meter per second, into V, that is 4 meter per second. So when you substitute this value, you will get equals to 23400 Newton. That is the propelling work. Now, to find out the second thing required is the overall efficiency. To find out the overall efficiency, we have to find out the work done by the jet and the total energy which we are supplying to the engine, because whatever we are supplying to this engine, 15% is lost here, then the balance is supplied to the pump loses 35%, the balance is supplied to this kinetic energy of the jet and it loses the 10% of that. The balance is this one, the work done which we are getting actually. So to find out the overall efficiency, first we will find out the work done per second, that is given as the force multiplied by the jet velocity of the ship. This is the work done force multiplied by this. So here we know the work done already. So 23400 multiplied by the velocity of the ship, that is 5 meter per second. So it comes out to be 117,000 Newton meter per second. Okay. Now, to the output of the pump, in this case, the output of the pump should be such that it gives a relative velocity VR at the exit and also take care of the loss of 10%. So the output of the pump should be equals to the kinetic energy of the jet plus 10% loss of the kinetic energy. So it should be equals to VR square by 2 for 1 kg we are considering. So rho A VR, that is the mass. So here it is 1 multiplied by, this is the kinetic energy by the jet, plus 10% of this, that is VR square by 20. This we have calculated here. So this must be equals to this one. So if you solve this, it will be 1.1 VR square by 2. 1.1 VR square by 2. Now, I'll remove this first here, the top area, then we'll solve here. Input to the pump per kg will be equals to the output of the pump upon efficiency of the pump. So we know the output of the pump is equals to 1.1 VR square by 2 and the efficiency of the pump is given as 65%, so divided by 0.65. So this is the output, this is the input to the pump here. Okay, now to find out the input to the engine per kg of water, input to the engine per kg of water will be equals to output of the engine. So this will be the input to the pump. So that will be the output of the engine. So 1.1 VR square by 2 into 2 into 0.65, that is the output of the engine divided by the efficiency of the engine. So here it is given as 0.85. So this is the input to the engine. Now to find out the input to the engine, we will substitute the values here. Is 1.1 into VR, that is given as 9 meter per second. So 9 square divided by 2 into 0.65 into 0.85. So it comes out to be 80.63 Newton meter per kg of water. So this is the input to the engine per kg of water. That means if we supply here 80.63 Newton of energy, so 15% will be lost, balance will be supplied to the pump, then the pump will lose 35%, it will supply remaining to the jet, and when the jet is coming out, during that process it will lose 10% as frictional loss, then we will get this much as the output from the jet. Now the total input, in this case we are calculated per kg, so the total input to the engine will be equals to mass flow rate of water, that is rho AVR, multiplied by energy required per kg, that is 80.63. So we will substitute the values. 1000 area was given as 0.65 multiplied by velocity VR was 9 meter per second multiplied by 80.63. So it comes out to be 471,685.5 Newton meter per second. So this is the input to the engine, and we know the output we had calculated earlier. So the overall efficiency of this combined jet propulsion system is work done. So work done we had calculated 117 kilojoules divided by 471,685.5. So it comes out to be 24.8%. So this is the overall efficiency. So in this case, only important is that you should be able to calculate this one in the reverse way.
Question number 3. A jet propelled boat moving with a velocity of 6 meters per second draws water amidship. The total area of the jet is 424 centimeters square. If the total resistance offered to the motion of the boat is 5890 Newton, determine 1. The volume of water drawn by the pump per second, and the second, the efficiency of the jet propulsion.
In the question number 3, it is given that the area of the jet is equals to 424 centimeters square, that is 0.0424 meters square, or you can simply write 424 into 10 to the power minus 4 meters square. That is the area given. It is given that the total resistance to the motion, that will be finally equal to the propulsive force. So resistance is given as 5890 Newton, and we have required to find out the flow of the water. Okay, so in this case we'll V. So F is given as 5890 equals to 1000 into 424 into 10 to the power minus 4 into VR. VR is nothing but V plus U. So we'll write here V plus U. U is given in the question as 6 meters per second. So 6 multiplied by V. So from this we can calculate the value of V as, if we solve this, V square plus 6V minus 138.9 equals to 0. So V will be equals to 9.16 meter per second. So the velocity, absolute velocity of the jet is 9.16 meter per second. So we can find out the volume of water drawn by the pump per second. Volume of water drawn by the pump per second will be equals to A into VR, because mass when we are considering, we are multiplying by this area and two velocities. This is the volume multiplied by the density, but here we are considering only the volume. So it will be A into VR, and VR now we know because V is 9.16 and U is 6, so it will be the sum of these two. So we can calculate this by substituting the values. The area is given as 424 into 10 to the power minus 4 meter square multiplied by VR, that is 9.16 plus 6. So it comes out to be 0.643 meter cube per second. So this is the first answer. Now to find out the efficiency of the jet, in this case it is given that the water is from amid-ship, that is the case 1. Water is entering from the sides of the ship, from this end, amid of the ship. So in this case the efficiency is given as 2 into V into U upon V plus U, or we can have work done per second divided by the kinetic energy. So here we will use directly the formula 2V into U upon V plus U square. So we will substitute the values 2 into V, that is 9.16 multiplied by U, that is 6, divided by V 9.16 plus U 6 whole square. So it comes out to be equals to 47.8%. So this way we can solve the, calculate the efficiency in this question. So this completes the jet propulsion of the ships. In this case, jet propulsion, we have considered the two cases when the water is inlet through right angles of the direction of motion of the ship, that is angle of the ship, and the case 2 we have considered when the water is entering from the front, that is in the direction of the ship, which is the direction of the ship. So in this case we have calculated the formulas, we have calculated the maximum possible efficiency, and then we have solved some 3 numericals. And now what is the application? This jet propulsion is used in case of the missiles, in case of the ships. Generally we are considering the small ships, then we are using this jet propulsion system. If it is a very large ship, then we are using the propeller, screw propeller type system, which is more efficient than this jet propulsion. So in the small ships only we are considering this jet propulsion. Thank you.